Hello, my awesome AP chemists. Today we're going to start chapter 18, which talks about thermodynamics. So if you remember, thermochem had to do with delta H. Thermodynamics includes delta H, but it also includes Gibbs free energy, and which is delta G, and also entropy, which is delta S. So as always, we have our learning objectives or learning targets. Make sure that you read those and use them as a checklist. And we're going to start with spontaneous reactions or thermodynamically favorable reactions. So spontaneous or thermodynamically favorable mean the same thing. College Board prefers the phrase thermodynamically favorable over spontaneous. But what that means is that it's a reaction that occurs without outside intervention. So I don't hook it up to electricity, for example, or give it a lot of force to get it to go. So, for example, if I have a ball on top of a hill, it rolling down, that would be a spontaneous reaction. Or if I have some ice and it's out at room temperature, melting the ice at room temperature would be a spontaneous reaction. Or if I have a gas in a container and it's filling that container, that's a spontaneous reaction. So it's just occurring. A spontaneous reaction does not mean that it's going to happen fast. So it has nothing to do with the kinetics or the reaction rates. So it could be a spontaneous reaction that takes years for it to occur, or it could be something that happens instantaneously. And I think that's why College Board doesn't prefer the word spontaneous, because for a lot of people, spontaneous means it happens quickly, when really those reactions are just, they're thermodynamically favorable. They will occur naturally, but it doesn't mean that they're going to occur fast. So for College Board, you want to use thermodynamically favorable. When we're talking in class, I'll use them interchangeably, spontaneous or thermodynamically favorable, just because spontaneous is a shorter word. So two forces of nature decide or determine whether a reaction is going to be spontaneous or not. The first one is entropy, and then the second one is energy. So let's write those down. So entropy has to do with the spread of matter. Nature prefers the spread of matter, and that has to do with entropy. And nature prefers an increase in entropy, and we'll define entropy in a second. And so nature would prefer if delta S is positive. That means you have an increase in entropy. Nature also prefers the spread of energy. And in terms of energy, that means enthalpy, right? That would mean a decrease in potential energy or a decrease in your enthalpy. And that would mean your delta H is negative, which is exothermic. So nature prefers the spread of everything, right? Nature wants everywhere to be equal, so it likes the spread of matter, it likes the spread of energy, it likes the spread of pressure, so pretty much the spread of everything. It wants everything to be equal. So let's first talk about the spread of matter. So entropy of the system, or entropy in general, is a measure of randomness or disorder in a system. And if you talk to a physicist, they'll tell you it's not quite that simple. There's degrees of freedom and all kinds of different things. For the purposes of this class, for AP Chem, we're just going to say entropy is a measure of randomness or disorder. But just know that the definition actually is quite more complicated than that. The symbol for entropy is delta S. So if you're finding delta of anything, like delta of the system, it's going to be final minus initial, and so it would be products minus reactants, just like we've always done with delta H. So nature prefers that things are disordered or random. If you think about it, it is much easier to make your room messy than it is to clean it up, right? If I ask you, hey, go right now to your room and make everything a mess. Take everything out of your closet and your drawers and put them everywhere so it's messy. It's probably going to take you like a minute to do that, right? Maybe a couple minutes. But if I ask you now, go back and clean up everything, organize everything, fold everything, put it back, that's going to probably take you an hour or two, right? So that's because nature prefers things to be messy. If you're making a salad and chopping it off and up and mixing it together, it's much easier to do that than if you already have a chopped salad and I ask you, take out all the pieces of tomato, put them all together, take out all the pieces of cucumbers, put them together, and so on. So nature prefers messiness and randomness and wants, things to be in 1,000 little pieces everywhere than organized as one. So it prefers that the products have more disorder or entropy or randomness than the reactants would. The ending materials need to have more disorder, and that makes it favorable. So if you think about it, if you're doing products minus reactants, final minus initial, if the products have more disorder, which is a good thing, it's favorable, the products are more messy, more pieces, then this would be a larger number than this one, which would be positive, and that is favored. So positive delta S of your system means that you are increasing in entropy throughout your process, and that is something that is favored. If your delta S is negative, that means that your reactants have more entropy or more disorder than your products. Your products are more organized, which is not a good thing. That's not favored by nature. That means entropy is decreasing as I go from reactants to products, and that is not favored. If you think about states of matter, if you're looking at solids, liquids, and gases, solids are the most organized of the three phases, right? They are close together, they are in rows and columns and stuff like that, right? Then liquids are a little bit more random, your crystal breaks, they kind of move around each other, and then gases are all crazy and random, right? They move really fast and they hit each other, hit the walls of the container. There's not really a rhyme or reason for their motion. And so gases have the most entropy, solids have the least entropy of the three states. In terms of dissolving, if I take a solid and dissolve it to get an aqueous solution, if you think about it again, a solid has a nice organized crystal, has very high order. Once it dissolves, your ions kind of move around in the water, and so those are not as organized. So aqueous solutions have more entropy than the solid form of your substance. In terms of number of particles, the more smaller particles you have, the more disorder. For example, if I have a nice vase sitting versus if I drop it and break it into 1,000 pieces, well, the 1,000 pieces have a lot more entropy, right? Have a lot more disorder. My nice vase as one solid piece is more organized. And so the more particles you have, when you go from reactants to products, if you have more smaller particles in your products, that is more favored, that is more disordered. So let's look at these and decide which ones have more positional entropy, which means more disorder. So solid water or gaseous water, which one would have more entropy? Well, gaseous water would, right? Because solids have this nice organized crystal, but gases are more random. How about oxygen gas under 1 atm of pressure or under 0.01 atm of pressure? What do you think? Which one would have more disorder? Something that's under a lot of pressure or something that is not under a lot of pressure, a gas that's not under a lot of pressure? Well, the more pressure you put on the gas, the more organized it's going to be. The less pressure you put on it, it's free to move around in any way it wants. And so less pressure means more entropy. Okay, how about the next one here? It says, in each of the following, indicate the positional entropy if the positional entropy is greater for the reactants or the products, and indicate the sign for the entropy for each process. So that's delta S, is it positive or negative? And also you want to answer whether the reactions are entropy driven or not. Entropy driven means that they are favored by entropy. So if delta S is positive, that means it's entropy driven. If delta S is negative, that means it's not entropy driven. So let's start with the first one here. We have CO2 gas going to CO2 solid. So we have a deposition process here. You're going from gas to solid. So first of all, which one has more entropy? The reactants or the products? And so gases have more entropy, right? So to answer the first question, it would be reactants. Next question is, indicate the sign of the delta S. So would delta S be positive or negative in this case? Well, it's going to be negative. You're decreasing in entropy as you go from gas to solid, so your delta S is going to be negative, which is not favored, so that means it is not entropy driven. Okay, let's look at the next one. So the next one, we have KCl solid. Looks like we're dissolving it to get the aqueous ions. So the ions are dissociating and being hydrated with water. So which one has more entropy, the solid KCl or the aqueous KCl? Well, the aqueous KCl has more entropy, and so the products now have more entropy. Delta S is positive because as we go from reactants to products, you have increase in entropy. And that would be a favored reaction, so it is entropy driven. So in terms of entropy, this reaction is good. Okay, next one, or process I should say is good. Next one, we have magnesium carbonate solid. I'm heating it, and it looks like it decomposes and turns into magnesium oxide and carbon dioxide. So what do you think? Which one has more entropy, the reactants or the products? Well, the products here have more entropy for two reasons. The first reason is that I go from one single particle on the product on the reactant side to two particles on the product side, or you can think of it as moles. Moles are particles. 1 mole here to 2 moles here. So this is my vase example. The more pieces I have, the more particles I have, the more disorder I have. The other reason is that this is just solid, so all your mass is as a solid, but here you have some solid and you have some gas, and gases would have more entropy. So in this case, the products have more entropy, and so your delta S is positive because you have an increase in entropy throughout the process as you go from reactants to products, and so this is entropy driven. That means it's favored by entropy. The third law of thermodynamics says that entropy of a perfect crystal is at 0 Kelvin is 0. So when it's absolute 0 and everything is frozen, and everything are perfect crystals, that's when delta S of a species is equal to 0. Any other temperature, any higher temperature, or any more complicated structure will have higher entropy. So if you have a really complicated structure, it's going to have higher entropy than something that is a simple crystal. And entropy is a state function as well. So if you look at your table of thermodynamics variables that you got, or thermodynamics values, I should say, that you got, we got this back in the Thermochem chapter in chapter 5. We also got another copy of it in this chapter. And it lists different substances. It's alphabetical in terms of what elements are in there. And it lists their delta H of formation, which is something that we've used before. And now we're going to look at the entropy, and then later on we're going to look at Gibbs free energy as well. So right now we're focusing on the entropy. You'll notice that when we looked at delta H's before, heats of formation, if you have an element in its natural state, its heat of formation was equal to 0. That is no longer the case with entropy. Nothing in this column is going to equal to 0. The only time the entropy of a species is going to be equal to 0 is if it's at 0 Kelvin and it's a perfect crystal. These values are at standard temperature, which are 25 Celsius, 298 Kelvin, and so you're never going to have a number that is 0 here. So you can look up the different entropy values here. On the test, of course, you're not going to be given this big table. This goes on for several pages, but you are going to be given the entropy values if you need them for the species that you need. So, as we had said, to calculate delta S for your system or for your reaction, you take the sum of the delta S values for the products minus the sum of the delta S values for the reactants. Remember the little degree sign? That just means at standard conditions, which are 298 Kelvin, 1 molar solutions, 1 atm of pressure. So we want to calculate delta S for these systems. Let's first predict. I have N2O4 gas going to 2NO2 gas. Let's predict if it's going to be positive or negative first. So what do you think? Would it be positive or negative? Well, if gases on the reactants, gases on the products, you have 1 mole in the reactants, 2 moles in the products, so 2 of smaller particles, and so that would be more disorder in the product, and so our delta S we would predict would be positive. So let's go ahead and calculate it and see if we were right. So we're going to say delta H for our reaction or system is equal to the sum of the delta S's of the products minus the sum of the delta S's of the reactants at standard conditions. So we're going to start, since products minus reactants, we're going to start with the product here, which is we have 2 moles of NO2, and we're going to use our table, the thermodynamic tables, to look up the value for NO2, and it is 240.04 joules per mole Kelvin. The units for entropy are typically energy per mole Kelvin, and usually they're in joules per mole Kelvin as opposed to kilojoules per mole Kelvin, because the values for S's are usually smaller. So notice that for delta H and later on when you use delta G, the values are kilojoules per mole, but here it's joules per mole Kelvin. So if we need to add them for some reason, watch out for that or do calculations with them. Okay, so that's my product, and then minus, I have 1 mole of N2O4 in the reactants, and the delta S for the N2O4 is 304.8 joules per mole Kelvin. So when you do your subtraction, you get positive 175.8 joules per mole Kelvin. And that's our answer. So we were right in our prediction. It is positive. Let's do the formation of ammonium chloride. So we don't have our reaction here. That means we need to write it out. So formation equation here. So we're forming ammonium chloride. So first of all, what is ammonium chloride? Well, ammonium is NH4 plus, chloride is Cl minus, so ammonium chloride is NH4Cl. Remember, a formation equation means that you're forming 1 mole of your compound from its elements in their natural state. So this would be made up of nitrogen, hydrogen, and chlorine, all diatomics in their natural state. And to balance it, we have to balance it so that we only have 1 mole of our product. So we need half of an N2, we need 2 moles of H2, and then we need half of a Cl2. So delta S of the reaction is going to be products minus reactants. So let's start with our products. We have 1 mole of NH4Cl. Oh, let's predict first. What do you think? Is that going to be a positive or a negative delta S? So we're going from 3 particles, right? 2 and half is equal to 3 particles to only 1. So that's not favored, right? Also, we're going from, these are all gases at room temperature, to a solid at room temperature. That's also not favored. So it seems like we're going from more disorder to less disorder, more entropy to less entropy. That means delta S is going to be negative. So that's our prediction. Let's actually calculate it. So NH4Cl is 94.6 joules per mole Kelvin. Then, oops, it's not a plus. So this is my reactant. Then we're going to subtract the product. So we have half a mole of N2. The value for that one is 191.6 joules per mole Kelvin. Then we have 2 moles of H2. The value for that one is 130.684 joules per mole Kelvin. If you want to round to like the 10th place in these, that is fine as well. Then finally we have half a mole of Cl2, and the value for that one is 223.066 joules per mole Kelvin. So products minus the reactants. If you go ahead and do your calculation, you're going to get the delta S is negative 374.1 joules per mole Kelvin. So as we predicted, it was negative. So this reaction is entropy driven. This one is not entropy driven.